So I left off talking about specifically what a one-to-one function is by definition, and I want to show you what a graph looks like so you can understand what it looks like from a graphical standpoint. What we have here is a cubic graph that is shifted 1 unit down. And the same thing here with a parabola. So what this kind of looks like is something like this. And this one is a parabola that's shifted 1 unit down. Now, when I said one-to-one, I said that each y can only come from one x value. And I want to show you how this second one fails to do that. If I plug in 1 into this function, I get 1 squared minus 1, which is going to be 0. If I plug in negative 1 at the same time, I get negative 1 squared minus 1. That's also going to be equal to 0. So I have two different x values producing the same y. So not every y value comes from a unique x value. So this is not one-to-one. Now, when we talk about testing for functions, we talk about testing with a vertical line test. With a one-to-one function, you can test with a horizontal line test. So this fails the horizontal line test. Okay? This is one that would be one that passes the horizontal line test. So this is something that's one-to-one. Now you might be asking yourself, what is the benefit for us to talk about something that's one-to-one versus not one-to-one? Well, the reason is that something that's one-to-one is going to be important for finding inverses, and here's why. If we look at a picture, we have an x value. It can be whatever we want it to be. And if we have a range value, we'll just call that f of x. We need some sort of rule to get from this point to this one. Okay? And we need some sort of rule to get back via the inverse. Okay? Whatever the rule is, it has to take each point and bring it back. If we have some other point that goes to the same y value, this inverse can't map back to both of them. So if we have something that maps to the same y, when you plug this one back in, it can't go back because this inverse has to be a function. So in terms of a domain and range, this has to have every single x value go to only one y value. That's why it's important to talk about things that are one-to-one, because if it's one-to-one, then it has an inverse. So now what we're going to talk about is how you find them if they have inverses. Now, there's a checking thing that you have to do with each one of these, and I'm not going to do it for the first one, but I will for the second one. So when you think about an inverse, you think about taking an x and mapping it to a y, and the inverse is doing the exact opposite. It's switching the idea around, taking the y and mapping it to an x. So when you find an inverse function, you're going to do the exact same thing. And you might ask, well, what does that mean? So I'm going to swap the two values around, x and y, because that's what we're doing. We're taking the y's and now mapping them back to x. So what we have to do is swap the variables around. So instead of looking like this, it now is replaced by this. X replaces f of x, and then y replaces x. So now we have a new equation that swapped the x and y, just like we're doing when you deal with an inverse function. So now we just have to solve this for y. So I'm going to times by 2, because this whole thing is divided by 2, so I got to get rid of that. So I have 2x equals 5 minus 3y. I'm going to subtract 5. So 2x minus 5 equals a negative 3y. Divide by a negative 3. And I get y equals negative 2/3 x plus 5/3. So my inverse function is negative 2/3 x plus 5/3. So we swapped f of x and x around, and then we just resolved for y. So that's the goal of this problem. You switch the roles because that's what an inverse does. It takes the y's and maps them back to x's instead. So we switch the x and y around. Now, I'm going to do the exact same thing with this next one. And you don't have this graph, but I'm going to show you something about this. So we're finding an inverse. We're going to swap x and y around. So what I'm left with is x equals the square root of 2y minus 3. So now we have to solve this for y, so I need to square both sides. And you're left with x squared equals 2y minus 3. Now we have to get y by itself still. We add 3. We get x squared x squared plus 3 equals 2y. Divide by 2, that means everything we divide by 2. So my inverse function is 1/2 x squared plus 3/2. Now, I'm going to deal with an issue that we have with this problem in just a second, because if you've paid attention very closely, you might have a question about how I might have just contradicted myself. But I'm going to check something real quick. I'm going to plug in the inverse, or compose the inverse in the original function. So I'm going to take the inverse here and plug it back into the original equation. So what I have is 2 times 1/2 x squared plus 3/2 minus 3. Distributing the 2, we get x squared plus 3 minus 3. We get the square root of just x squared, which is x. So the first part is good. So now I have to check the other way around. So I compose the inverse with the original function. So 1/2 times the square root of 2x minus 3 squared plus 3/2. So we have to square first using orders of operations. That clears out the square root, but I still have this all in parentheses. Now I have to distribute the 1/2, so I have 1/2 times 2x, which is just x, minus 3/2 plus 3/2. Those cancel out, you're left with x. So these both work. And you might be asking, well, where is the contradiction that I've just said? That's a parabola. And most parabolas, all parabolas generally have, or they all have the same shape. This is a parabola we just got done doing and solving, and we showed that it's not one-to-one. If it's not one-to-one, then it can't have an inverse. So we just found a parabola that has an inverse. It seems like I'm contradicting myself when I say this, but let me explain to you how this is dealt with. Okay, if you look at this function, hopefully you can see by now that you can't take the square root of a negative number. So this expression can't be negative. And if I solve this, I get x has to be greater than or equal to 3/2. So this function starts right here. And the graph actually looks like this. Okay, so the starting point for this function is at the point 3/2, comma 0. We can't let x be greater than, or it can't be less than or equal to, or excuse me, we can't let x be less than 3/2. So how does this fit with a parabola? Well, if we look at this, we're switching the inverse function around because now the y values are treated like x values. So the smallest y value we have on this graph is 0, and then it goes up because you can't take the square root of a number and get something smaller than 0. So we are actually going to start this parabola right here. We're going to start it at this point. Okay? And the point is 0, comma 3/2. And we are going to just go from there to the right. So I didn't draw a complete parabola. I just dealt with values that were 0 or above. Because again, in the original function, y couldn't be smaller than 0. So when you think about the inverse, and we're switching the values around, so the y's in this is actually the x in this function here, because it's the inverse. The smallest we got was 0. So the smallest that this one can be is 0. It can't go into the negative because we didn't produce any negative values in this function. So the way that you deal with this is say, I can't deal with any values that are less than or equal to 0. And then I draw an incomplete parabola. This will pass the vertical line or the horizontal line test, so we don't have to deal with this being non-one-to-one. And I will talk about how you look at this from another example. But you have to make sure that you understand that the y values in an original function behave like the x values in the inverse function.